I think we are recording. Okay, fine. So hello and everyone, and welcome to the week 4 of this live sessions for your course Intro to
There is
Machine.
an echo.
I'm sorry.
There is an echo and a
Is it
prominent one.
okay? Is everyone having the echo? Hello. Can people respond so that we'll understand? Is it at the transmitting side or the receiving side? No. Okay. It's clear. Fine. Then I think we'll go ahead. So Bhushan, you might want to.
Clear now.
Okay, fine. Okay, great. Fine. So we'll move ahead. Okay, so I thought to do the assignment 3 questions. We have the solutions also now, posted by NPTEL. So we can go through them, and then we'll have some general discussion about joint and condition probabilities. And of course, any doubts anywhere else also you can ask ahead. Yeah. So start with the assignment questions, right? So the first question. K nearest neighbor is non-parametric eager, non-parametric lazy. What do you think is the answer, and is it right or not? The explanation. Any doubts here? No. And fairly straightforward thing, right? It's non-parametric because again we don't have any parameters to be learned in this algorithm as such, and lazy because we're not learning anything during the training phase. We do everything at the testing phase only, right? Then you've been given 2 statements. Fine. In case of very large value of k, we may include points from other classes into the neighborhood. In case of too small value of k, the algorithm is very sensitive to noise. So anyone disagrees that both of them are true, or any clarification required? No. Okay. So yeah, very clearly. So if you have large value of k, we're taking more and more space around the point. So therefore, points from other classes will also be in your neighborhood. And too small value of k, you will get sensitive to noise because as such, because your points are sensitive to noise, whatever you've gotten is a noisy data. So therefore, if you take a very small value of k, it's very likely that you will be tuning or getting results based upon the noise that you saw, but not on the real data that exists, for example. Right. KNN algorithm does more computation on test time rather than train time. Again, that's very true. We just discussed. Train time, KNN does actually nothing. It's just storing the data. And by test time, they then looks at the distances and computes the nearest distance, etc., etc. So all of that happens during the test time only. That is, when a new sample comes in, how do you classify? That's happens at the test time. Question 4. So we have 3, KNN sort of boundaries given, and we want to understand which one of them is basically higher or lower k, right? So I hope people will agree that C is the answer, right? Any clarification required, you can let me know. So again, such questions ideally, so the way to solve it is you should basically look at the boundaries, right? What is happening at the boundaries, because that's the interesting part of, I mean, in KNNs, right? Because k, the value of k starts affecting at which level you classify your points, right? So if you see here, for example, this particular point, which is, let's say, all these red pluses in this area, they all became classified as blue pluses, right? And that's possible only when you have large value of k, right? Because at this point, for example, because there are more number of blues around it, so it got classified as blue plus, right? And if you see here, you have if you see here, like you have this sort of gaps in your decision boundary. So all of these happens when your k value is very less, right? So for example, there was small plus here, and so therefore all these points near the plus got classified as this red plus, right? So therefore, so boundaries, you can look at the boundaries, and that'll give an intuition as to what value of k was running there, at least in comparison to the others, right? Um, which of the following necessitates feature reduction in machine learning? So again, irrelevant and redundant features, yes, because if something is irrelevant, we don't want it to be part of your decision making algorithm. Again, redundant features in the sense they don't provide any new information compared to other features. So there's no point having those features in your data. Limited training data, again, yes, because when you have large number of features and you have less data, then you will start hitting your curse of dimensionality, or you start overfitting. So if if there is some possibility to reduce the features, that is feature reduction, you would ideally want to do it in case you have limited training data. And limited computational resources also, that is true, because more number of features means you'll have to do more number of computations. Again, very simple sort of proportional relationship. So if you have less features, then you will have then you need to compute less, and therefore there could be a value add to this particular problem. So the right answer is all of the above. All right. Question 6. Suppose you have again you have some points here which are classified as plus and minus class, and this is scatter plot of those plots in a 2D space. And now the point is you want to know whether x equal to 1 and y equal to 1 point. How will that get classified, right? So if you see here, x equal to 1, y equal to 1 is somewhere here, right? So the nearest points, if you think about it, it's all of those are plus the class plus belong to class the plus class. So therefore your 3 and n will actually say will actually be classified as plus class. All right. Then what is the optimal number of principal components in the below figure? So if you see here, the percentage of variance explained, right? The cumulative percentage. So that what it means is if I take 30%, sorry, 30 principal components, I'm able to explain almost 100% of the variance in the data, right? So there is no point taking anything more from there, right? So 30 is the best in this particular scenario, right? Generally, you will not find this sort of thing. Generally, what will happen is you will have a curve which will peak only at the maximum number of features, right? So it'll have something like this. I think I might have done this, but question 7, right? So it'll have something like this. Let's say if you want to plot cumulative percentage of variance and number of principal components. So let's say the number of principal components maximum is a number of features that you have, right? So let's say number of features you have is, let's say, some f. So exactly at f you will have 100%, generally speaking, right? So you will have something like this sort of curve, and then it will hit exactly one only at f, this one. So generally what you do is you say, okay, 95% or 90% variance, what can explain? You'll take that number of features and go ahead, right? Depending on how much your error tolerance is. So our correct answer is C. Then instead of using all features, we use only k dimensions with the PCA. So then what is the right answer in our case, right? So if you see about it, so the point is when you have higher k, that means, I'm sorry. Yeah. So if you have higher k, it means you're taking more and more number of dimensions. So if there is noise in the data also, you will be using even that particular data also into your dimension, into your decision making process, right? So ideally, so that means you're taking noise also into consideration. That means you'll be less regularized, right? Because regularization means basically trying to overcome that sort of noise that is there in the data. So higher value of k means less regularization, not the opposite. All right. Any doubts till now? Very silent today. All right. collaborative filtering, items are recommended based on similar users, not similar items. Similar items you can do, but it's not called collaborative filtering anymore. I guess there are some other names for that. So collaborative filtering is basically for similar users only. Major limitations. So one thing is, yes, cold start, right? Because the point is that if we have very few transactions, so therefore it will be very difficult to find similar users for them. And again, see, it's not just the point of very few. It's possible that many users don't make any transactions, zero transactions. So then what do you suggest them, right? So that becomes a problem, and that's something called as cold start. Ideally, what is done is you just give them ideally you can just give them you know some like general items which trend well throughout all users, right? For example, let's say you start with that and then you continue, right? So question 9, no. So collaborative filtering is basically on users only. At least that's what I understand. It's not on items. Item recommendation that is there, but for a new user, that's called collaborative filtering, and you use similar users basically. Again, similar in the sense of like similar transactions that you have done in the past or that sort of a thing. That similarity is a different definition, but is that clear, Isan? Okay. Um, no. So see, you can recommend based on similar item, that sort of a thing. That is fine. But collaborative filtering based recommendation means similar users. You look at patterns of similar users. What have they interacted with the item? That is recommended to this new user, to this to a user that you're trying to recommend to.
Just an interruption. I just want to know whether others are able to hear the guest speaking. I'm not able to hear. I'm only able to hear you, Mr. Jain.
Guest speaking? No. There is nobody speaking currently. If I'm
No,
not
when
wrong.
they are asking a question to you about question 9 or so, or is it okay on chat?
It's on the chat, Bhushan.
Okay.
Yeah.
In between, the voice is getting blurred and we are having an echo. I don't know from where.
Sir, your
So,
network is not that clear. I guess that's a problem. You become blur suddenly. You become blur suddenly, sir. I mean that video.
oh, video becomes blurry. Is it okay? 1 second. I guess that's there's an issue with that. 1 second. Wait. Um, wait a minute. Yeah. Is it fine now?
Yes, sir.
Okay. So ideally now video should not become blur, and I think Varun is confirming that he can hear, and the questions are on chat, right? Currently, at least. If you have any question, feel free to unmute and ask. Not a problem. Okay. Fine. Okay, we'll move ahead with the next question. Question 11. Which figure shows the most probable PCA component for directions for the data points? So again, this should be very clear from the different ideas of PCA. The point is that it captures maximum variance, the direction of maximum variance in the data, right? So as you can see, along this direction, you have a lot of variance. That's the first principal component, ideally, and then along this dimension, you have another level of variance coming in, and the hope is that these two should be orthogonal in nature, right? So that also you can use to understand which of them is right? So question A, right? So answer is A. So again, so orthogonal and total variance of the data should be maximum. All right, then suppose that you wish to raise a number of okay, so again the same sort of idea here. So higher values of k means that you're preserving more and more characteristics. That is basically you can end up becoming more and more you can end up including more and more noise. So therefore it means less regularization, not the other way around, right? Question 13, anybody wants to answer? What, why this is so correct answer is given as B, 2 and 3, but why is that?
It is about 2 and 3. I think, see, suppose you are given 7 plots, you want to compare the Pearson coefficient between variables of each plot, which of the following is true? See, in the first one, we have the highest Pearson correlation. And on the last one, we have a highest but negative correlation. So numerically the lowest, -1.
-1, right, yes.
Okay, so the second one is lesser than the first. Third one is almost lesser than the second. So it is in the descending order. And the fourth one are almost correlation 0. Then it starts to get correlated in the negative direction. So that is why the correct answer is B.
Right, correct, right. So you need to remember that Pearson correlation can be negative also, right? So we are asking only about the Pearson correlation coefficient as such. So this seems to be almost 0 correlated. So this becomes 0 correlation or near to 0, and this is a perfect negative correlation. So as let's say this dimension, let's call it x and y. As x increases, your y will surely decrease. And here why it would be less than this is because of the fact that it is not perfect as such, right? Because there is possibilities that if you increase x, if you see, for example, these 2 points, right, the amount of decrease is not that clean, right? So so again, this is what you will deal with in general data also, but the idea being that there is some noise present in the y dimension or the x dimension, which is causing the Pearson coefficient to not become exact perfectly -1, but it will be highly negative. And similarly with these plots, right? So it is negative, but again, not that negative because there is some noise present in the data. Similarly here, right? All of these will have positive correlations, but this is almost like almost like noise free at all, zero noise sort of thing. Here again, noise increases, so your Pearson correlation will decrease, but it will remain positive because there is a general trend of positive, association between x and y, right? So the answer is B. All right. Then 20 class problem. What's the maximum number of discriminant vectors that can be produced by LDA? So answer is 19. Again, this should be straightforward because LDA tries to project the data into a n-1 dimension space where it can, separate these classes easily. Okay. Then let's come to yeah. So which of the following situations collaborative filtering is appropriate? So you manage an online bookstore, you have book ratings from many users. For each user, you want to recommend other books he or she will like based on previous ratings and other users' ratings, right? So this is very, again, textbook example of, sorry, definition of collaborative filtering, because you want to recommend something based upon other ratings and other users' ratings, right? So that's the idea of collaborative filtering. Here you want to, so you have an online bookstore, you have book ratings, you want to predict the expected sales volume as number of bookstores as a function of average rating of a book, right? So you want to know if there is some sort of relation between the average rating of the book and the sales volume that is there for that book, right? So again, there's no collaborative filtering as such. There's no recommendation happening here. It's more of a prediction sort of a problem, right? Because you want to understand whether how this function varies, right? Is it linear? Is it more complex, etc., etc., right? Okay. So any questions in this assignment solution? Otherwise, we'll move on to the next topic.
Sir, fourth one, can you just explain, sir?
Fourth one. Yeah. So as I said, see, the idea here is that when you want to understand the what k value is there, you need to look at the boundaries. At boundaries, what is happening? So if you see for this particular example, all these red pluses are getting classified as blue pluses, right? So which means that because you have higher k, now because for this particular point you have more number of these this blue pluses around, so all of the points which come up in this region, they get classified as blue plus. So this clearly could mean that there is a higher value of k, right, than compared to, for example, let's say this, right? And one more idea here is because your decision boundary is very fractured, in the sense there is it's not very smooth. So if you see here, in this region of this brownish color or whatever, right, there is some yellow patch, and that's probably because of the fact that you have we have these red pluses around it, right? So when you have small k, this will get all the points here will get assigned to this plus class, which is your yellow, right? So very likely that this will have a low k value, right?
Okay, sir.
Yeah. Again, one very simple thing is you have k written here, but then nobody can know that is that k the same k or some other k, and so on. So uh, I would suggest understanding. Okay, question 6 is it? So yeah, question 6. The idea is, see, you have some points which belong to plus and minus class, and that's the same point which have been plotted on this particular 2D space. Now, what is the question? The question is, you want to predict the class for a new data point, that is x equal to 1, y equal to 1, right? So that's possibly something here, right? This is the point. So there's a new point that's coming up here, and you want to use only 3 and n, that is 3 nearest neighbors only, again using Euclidean distance only, right? So very clearly, if you were to draw, look at the 3 nearest neighbors for this particular point, is these 3 classes, is these 3 points, right? Because this has a distance of 1, again this also has distance of 1, again distance of 1, right? All of them are farther apart. So the 3 nearest neighbors for this particular point, x equal to 1, y equal to 1, belong to plus class. Now because they all belong to plus class, this point will get classified as a plus class, belonging to the positive class, right? That's the intuition. Intuition and the way you will solve this problem, Adil. Any further doubts?
Yeah, I have one on 14th question.
14th question.
Yeah,
Go ahead.
so this is 20 class problem. That is, Y label has 20 different plus minus. There will be 20 such cases, A, B, C, D till 20. Correct. So why is it C minus 1 basically? It's not about means it attributes can be 100 attributes, but ultimately there are 20 classes. So why is the answer 20 minus 1?
So the idea is that it will ideally, it is what I remember from LDA is it will just project all your data onto something n minus 1, right? Where n is number of features actually, number of classes actually, right? Because
Uh,
in that space, then it'll try to point which which class the particular point belongs to,
So
right? That's
actually, dimensions we usually here associate with input vectors. The input like x1, x2, the attributes. So
okay.
here it's a label. It's saying label values are 20. That
Okay,
is my understanding correct? The label values like A, B, C, D karke, there will be
correct,
20 label values, and now nothing is said about the attribute. That means the dimension where we are working in.
right,
Correct? Is my
correct.
understanding correct? So it
Yes,
can be a 200 attribute problem, so 200 dimension, or it can be 10 dimensional problem.
yes.
Now discriminant vector, what ma'am showed us in a simple example was a two class problem wherein one vector was able to do that. But in a say, give us an example of three class pe how two vectors it is coming. Like, can you show that? Like, So it's not like dimension related problem what I'm thinking. This is C minus 1. So
So you need, so basically how many discriminant vectors you need, that's the problem, right? So how
yeah,
many
yeah. So
so let's say if it is a 100 dimensional problem, you need 19 100 dimensional vectors to solve this problem. What LDA is.
so how is it coming? Like I'm not getting any idea.
Okay, so just give me one moment. Uh, I can just pull up something and show it to you instead of uh,
Sir, the
right.
best way is you take two attributes, two-dimensional data and three classes, and then graphically maybe you can illustrate how
Yes,
it
yes.
works.
That's exactly what I'm showing actually. So let me yeah,
I'm just getting confused with terminology.
yeah, go ahead.
What is now the difference between this class and features? Is it the same?
No.
No. Who was it previously who answered the question?
I answered class is Y label. That
Yeah.
one dimensional label, how many different values it takes. For example, Y label can be positive, negative. Play tennis or no play tennis. That is two class problem, what I understand. Correct, right?
Sorry. Yeah, correct. So play
Yes, sir.
tennis and don't play tennis is two class problem. Correct. So okay, one second. So let's say 20 class problem. How do you understand something like that? Is
Yeah.
let's say you have images of different fruits and you're given that there are 20 fruits only in this particular
Hmm.
image, right?
Hmm.
Instead of you have some
Yeah.
1,000 images or whatever, right? Now the problem is you need to classify these images into one of these 20 fruits, right? This is a 20 class classification problem, right? Because you have 20 possible classes and you need to assign each image to one of these classes, 20 fruits, right? Now the image themselves can be anything, right? So basically it is basically it could be, for example, a 32 cross 32 image or a 64 cross 64 image or anything. So this is the number of features that the input has, right? That's the number of features that the input has. So this is basically 2 power 10. This is 2 power 12, right? Number of features that exist. So this is the number of features. This is the number of classes the problem has to solve into, right? So when you talk about supervised learning and your classification problem, so X and Y is there, right? So this X is the images, Y can take one of 20 values. This in this case, one of 20 fruits. Yeah. Class or target
What
same.
is
That is,
X and Y you said?
I'm sorry.
What did you say? What is X and what is Y?
Yeah, X is the image, right? In this problem that I
Okay.
show, X is the image, Y is this classification that you want to do, right? So Y will take any one of these 20 values, for example, orange, apple, whatever, right? So one of these 20 values.
So Y is the class.
Y is the class, correct? Y is the class.
And X are the features.
Correct. X are the features, input features that go into, or
So
attributes.
what are the
Again,
input features which go into an image which you can classify it as a class?
correct. Yes.
Pixels.
Okay. Now understood.
Yeah. So
Sir,
again,
32 is a pixel here, right, sir? The image.
yes. So the image
Different.
is a 32 cross 32 image means 32 cross 32 number of pixels are there.
Okay.
Those number of pixels is 1024 pixels you will use to classify the image into one of these 20 examples.
Okay, sir.
So yes, Sankari, you're right. Class or target is the same. Features and attributes are again similar. So this image that I said, you can say it as attribute or feature. All of this is the same. Yeah.
Or
Getting.
dimension.
I'm sorry.
Dimension, feature, attribute are same. Output, label, target are one same, right?
Label is also correct. Label, target is also fine.
Target,
Yeah.
output, all same synonyms.
Or output, yes, because yeah, output has to remain in the target space. So, but dimension is not same. See, dimension is a very general idea. Dimension is basically something which tells you about where does that that particular random variable lie. For example, this x, this image that I was talking about. If I'm taking a 32 cross 32 image, the dimension of x is 2 power 10, right? Because I have 1024 pixels, right? Now the dimension of y, okay, this is for dimension of x. The dimension for y can vary based on algorithms, but the idea is still being it's a 20-dimensional value.
This is one dimension with 20 discrete values, right?
Yes,
One
that's
dimension with what 20 values possible.
again. So I wouldn't phrase it that way, because when you say one dimension, inherently I would say it means that there is some ordering in those dimensions, right?
Yeah.
Now,
Okay, okay.
so
No.
let's
The other way, can we get binary value? What a computer counts.
I'm sorry.
Can it be implemented as a binary value that has been read by the number of pixels?
Binary value that has been read by as a number of pixels. No, no. Why binary? I mean, we can. I mean, this could be a grayscale image. Then you will use something between 0 and 255, right? Yeah. So it's okay if you're digressing, but just a moment. So let's say if I have a mono chromatic image, right? What does that mean? It means every pixel is only either black or white. So then your point makes sense, right? Because then I can encode every pixel as 0 or 1, right? Black, white. That's simple. Let's say if it is a grayscale image, and generally grayscale images are understood in 8-bit, using 8 bits that they're coded. That means total possible values here are 256 values, right? So 0, 1, 0 to 255.
Differentiation between monochrome and grayscale. Can we take in it as monochrome and RGB?
No. So RGB is, again, it has 3 channels of these grayscales. So RGB
So
images.
can
So
we count
RGB.
or green or black as one grayscale?
Correct. So you have RGB is basically red, green, and blue, right? So each of those are again coded using 8-bit. So therefore you will have 256 into 3 possible, so 256 values per channel into 3 channels.
Great. Thank you.
Possible values, number of possible values, right? This is the idea. Now, why I was a bit hesitant to tell y belongs in one dimension is again for this reason. So let's say if I say x is a one-dimensional quantity, right? What does that mean? It means if I say x equal to, let's say 2 and x equal to 3, then I have an ordinal relationship between them. 3 is more than 2, 2 is less than 3.
Yeah.
Now, but
I got that.
yeah, yeah.
For that ordering issue, you didn't wanted to classify as one dimension.
Correct. Yes. Because you cannot give a clean idea about this which fruit is more. So ideally, I would say it lies in a 20-dimensional space. Okay. I'm just trying to get this one example so that it's easier to put it out. This one. Just a moment. So this is what I get, for example, something like this. So this is again using LDA, right? So where is it? Yeah. So let's have 3 classes, right?
Yeah.
And so basically, I'll have 3 Gaussians. Basically, each of them will be Gaussians,
Mm-hmm.
and I will. You're saying we'll need just two, is it? No, no, no. So
I was seeing this only three. It will require three at least. Means for three classes, three vectors. But over the internet, everywhere it said C minus one.
right, right.
Uh,
Okay. So let's see how it'll get classified, right, at the end of the day. So let's say I have a point somewhere, somewhere here, right? I'll look at the where it is closest to, right? So I don't really need these three. So these are actually decision boundaries, but at the end of the day, I just need two points. So if you see here, let me just think about this 1 second. Mm, So let's say I have some points red here, right? And green here, and let's say blue. So then what I can do is I can actually, to cluster between these two objects, I can use this dimension, right? And then to cluster between these two objects, I can use one more dimension, right? Something like this. I can basically project on this space is what I'm saying. Right? So if I do that, so then that's enough, right? Because then I can tell, okay,
okay. I got it.
right?
Projections it will take. Correct.
So that's the thing. So hence I need just whatever number of classes minus one is enough at the end of the day. Okay. Okay, fine. So this is assignment 3 questions. Any other questions?
There only one. Seventh one I could not. There was a network issue here. Can you please
Sorry.
tell seventh one, sir?
Sure.
That.
Question number 7. So this I mentioned. The idea is, see, in general, basically, whenever you are using more and more principal components, the amount of explained variance goes on increasing. This again, I guess, should have been covered in the lectures. But the idea, so what are we saying here? We're saying that when the number of principal components I use 30, I'm able to explain 100% of the variance, right? That means I'm able to perfectly reconstruct the data just by using the first 30 principal components. So therefore, I did not keep all of these. For example, now this would come somewhere around 42, for example, right? So I did not keep all the 42 dimensions. I can project them to this 30 dimensional space and still not lose any information. So therefore, it's best to have this 30 as a right answer, right? Is that correct?
Okay, sir. Got it.
Additionally, what I was saying was that will not happen in real data. So what will happen is only when you use all principal components, you will actually reach the 100% mark. So what we generally do is we say, okay, 95% explained variance or 90% explained variance. How many of our principal components explain that amount of variance? We just take that number and move ahead. Okay, fine. Any other questions? No? Okay, fine. So we'll move on to the next topic. So I just want to discuss a bit upon this joint and conditional probabilities, because I guess a lot of this Bayesian networks, everything deals with this idea. So I mean, if everything is fine, then we'll move on to some other topic. But let me just ask these questions to you, right? So let's say if I have a probability of A B, right? So this is the joint probability of A and B. So how can I get this conditional P of A given B? How would I evaluate this? Any thoughts?
I think divide probability of A and B divided by the probability of B.
So you're saying probability of A
intersection B.
Okay.
Divided by the probability of B.
A intersection B, probability of B, right? So okay, is this equal to probability of AB?
This will be equal to, I think, probability of AB. A given B.
So sorry, I mean just the numerator. I mean. So
yeah, that is AB means PA intersection B, right?
correct, exactly. So this is the good probability of A intersection B.
So it will be PA A given B into probability of PB or probability of B.
I'm sorry.
PAB is nothing else but PA intersection B.
Right.
Therefore, PAB will be probability of B into the probability of A given B.
Right. Correct. Yes. 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 Correct. Right. So this is how we are coming to here, right? Yeah. So yeah. So this is right. So then you can write probability of AB as probability of A given B into probability of B, right? Similarly, can somebody tell me what probability of B given A would be? Quickly, I think this is all straightforward stuff.
Same thing. It will be the probability of B intersection A upon the probability of A.
Right. So is this equal to probability of AB by probability of A?
That is because yes,
Yes.
because
Yeah.
probability of AB is equal to probability of BA.
Correct. That's it. Right. So this intersection is symmetric. So this is the thing about probability of BA. Right. So this is all fine. Now, okay. Let's say I give you probability of AB. Can I find the probability of A? How do I do that? How do I get probability of A? So how do I get the individual component probability given from the joint distribution? It has a special name for this sort of distributions.
Probability of AB divided by probability of B divided by A.
No, that is, yeah, correct. I mean, yeah, you could just do the usual division. I'm just saying that without these conditional probabilities, I'm just giving you probability of AB, right? I want probability of A. How would you go about doing this? So let's say I'm giving you, all.
Sir, to get probability of A, we have to marginalize the probability of AB with B, all B's.
Okay, so can you give me the mathematical
sigma of a probability of AB for all B.
For all B, right? Yeah, this is called as marginalization.
The law
right?
of total probability.
Law of total probability, right? Law of total probability, yes. So that's the idea, right? So basically, if you have any joint distribution, if you want the distribution of one single component, you have to just marginalize the remaining all ideas. Similar thought process into this. So probability of AB and summation over all possible A's here you will do here because I want the probability of B, right? So this is marginalized. So this is called marginal probabilities. These are called the joint probabilities, right? This is called marginal. This is called joint, and this is called conditional.
Actually, on the ground level,
yeah,
I don't understand the difference between conditional and joint probability. Isn't a probability of A and B and the probability of A given B the same? Because I'm giving you B means I want the B and A both, the intersection of that. Isn't it not the same?
No. Okay, so think of it as distributions, right? So probability of A given B is basically if I give you B, is there any change in the distribution of A? Right? So let's say before anything in your let's say in the universe, right? So you had some probability of A with you, right? Now I'll tell you that okay, there's some event B happened. B happened, right? You're interested or you want to know how did this A probability change. So that is understood by probability of A given B.
Okay.
That's conceptualized as probability of A given B. Yeah. Yeah.
Like suppose, a real life example,
Uh-huh.
you have three signals, red, yellow, and green.
Okay.
And you have a madman walking on the street.
Right.
Okay. So we want to calculate the probability of how he's going to be hit by a car.
Right.
Obviously, when the probability, if you are given the probability of the red signal, he's going to be hit less than yellow signal than green signal. Now, in that case, what this will be? This will be a conditional probability or a joint probability?
So it will be conditional, no? Because you want to understand for each scenario, let's say, if you want to understand, right? For example, let's say, okay, so A is, probability or the event A is, for example, let's say, um, a madman getting hit, right, by a car or whatever, right? Now, the point is, before any information about the signal, that's the point where you need to understand B, how does it come, right? So before any information about what signal happened or is there a signal, etc., whatever, right? What is the probability of a madman getting hit? That is something that you might have with you, right? Let's say in general, what happens? What is the probability that a madman gets hit, right? So let's say the probability is something like 0.3. Okay. Now, then if I say you, okay, now B has happened. Now B, you need to specify what exact B happened, right? So let's say if B is, for example, let's say red light, was active, right? Then the probability of A given B falls down to, let's say, 0.001, right? Because the idea being during red light, again, we are just conceptualizing one traffic road and all of that, no multiple signals, etc. Right? So then the idea is probability of A given B will be very, very low. Now, let's say if B was, for example, let's say green or green, right? Then the probability of A given B could be actually more than 0.3, right? Because now they're continuously increasing. So, for example, it could be just as high as 0.8. Now, let's say if B is, for example, let's say yellow or whatever the color is, some other colors. So, let's say P of A given B would now be, let's say, closer to 0.3 or let's say 0.25 or something, right? Something like that. That's the idea. So now the point, so again, this is where we're saying, okay, probability of A, you can calculate it as probability of A into B overall B, right? And then this can be now written as you rightly mentioned before, right? So it can be seen as summation over B, probability of A given B into probability of B, right? Now we're saying that over all these possibilities that B could occur, this probability of A was 0.3. So again, you can infer, what the right properties are and all of that. That's a different question, but you get the idea.
Yeah, I get the idea. Only I just want to ask one last question. That is, probability of a man getting hit when the signal is green, you are saying is 0.8. Don't you think this will be the highest and therefore that will be equal to 0.3?
No. Okay, see, that's exactly what the point here is. See, probability of A represents the average of these conditional probabilities, averaged by this particular probability. Right now, see, it's possible that your green light is not on, very high amount of time. Okay, so the probability that B itself happening is so low, right, that the probability of A given B, though it is very high, that product comes down to be very small, and therefore then other terms probably they take over and the probability comes down to 0.3.
Okay, so if we want to get the joint probability distribution, then we need to know what is the probability within, say, 24 hours of red light and of green light and of yellow light.
Right. Yes. Yes. So joint probability basically tells you all possible combinations, what is going to happen, and everything. Now, when you want to make questions, questions like if you want to answer questions like, okay, if this happens, then what happens? Then what's the probability? Those sort of questions are basically conceptualized as conditional probabilities.
Okay, understood.
Okay. Yeah, so this is the idea of marginalization, and then joint, and then conditional probabilities. Now, so again, this gives you the idea of Bayes theorem and all of that, right? So we know what Bayes theorem is, for example. If I know what is A, and I want to know the probability of B given A, I can conceptualize. I mean, it's equivalent to calculating this sort of probability, right, by probability of A, right? And then what happens is, now this probability of A can now be seen as a marginal over all the possible values of AB, right? And then you could extend this further by saying same. So probability of A given B into probability of B divided by sigma over B. This again you can split it as probability of A given B into probability of B, right? This is exactly your total probability formula, that sort of a formulation, right? Um, okay, so now let's say I have probability of A given BC. How do I get the appropriate what you can say Bayes theorem for this in terms of conditional on C? Any thoughts? So I want a Bayes theorem sort of representation for this probability, right? Such that all terms are conditional on C only. So how would you get that? Anyone wants to start off?
I think I would do it in two steps.
Okay.
First, I would do it like, that probability of A into the probability of BC given A upon probability of BC.
Okay.
And then take this BC given A term and factorize it further.
Okay. How
And
would
say
you?
BC, that will be now BC given A would be uh, how would be, that is probability of BC into probability of A given BC divided by probability of A.
Okay.
And then if you plug it in there, you will get probability of BC and BC getting cancelled.
Okay.
And then you would have probability of A and probability of A also getting cancelled, I suppose.
All cancelled. 1-1.
Right, because so this was a question, and you'll come back to the question again.
Yeah.
Yeah. So everything
No,
will get.
sir, how do you compute probability of BC given A?
Okay. Why not? You can't. Why can't you compute that?
Probability of BC given A. How do you compute that?
No. Okay. So this is basically a joint conditional probability. So what you want to know here is basically how these two variables are. How are their probabilities together changing when A is given, A is known, or A happens, right? So again, you can use this example for use this idea for example. What I will do is I'll say C is um, signal on the opposite road, right? something like this, right? So now, now the question is, let's say something like this, right? So, okay, let's not do this example. 1 second, so to get it more clear. Okay, so let's say C is not a madman. Okay, some rational man, rational rational man going on the road, right? What's the probability of this guy getting hit, right? Yeah, probability of getting hit, right? So I want to know now probability of AC, that is both A getting hit and C getting hit, given some B value, right? Given, let's say the signal is red, the signal is green, the signal is yellow, that sort of a thing, right? So what I'll have to do is I'll have to specify all possible conditions. That's the only way to do these sort of things when you have discrete random variables. Otherwise, you have to specify the functional form and stuff like that. But you got the idea. So then what you'll have to do is you'll have to understand things like these. So let's say so probability of A given A getting hit and C getting hit when, let's say, the light is red, right? So that will be like very low probability, right? Because there's no cars on the road, so the rational man will also not get hit. He will move, but he will not get hit. But right, and same thing with the madman. Well, for example, let's say green, right? In green, the probability of the rational man getting hit is still low because he will not move now. Yellow, for example, you can say, okay, a rational man would try to cross the road because he wants to cross the road, right? Again, hence rational in quotes. So then the probability of AC, like this madman getting hit and rational man getting hit, could be a bit more, right? Together when you looked at other cases, that sort of a thing. Is that clear, Krishna?
Yes, sir. Yes, sir.
Okay. Okay. Coming back to the question. So yeah, that's how you would calculate something like this. This is a joint conditional probability. Okay. So how would you? Okay. So coming back, how would you solve this problem? So again, go back to first principles, right? So I'm saying I want all terms only conditioned on C. Let's say I don't have any joint probability with C. I have all the probabilities, but all of them are conditioned on C, right? So then how do I apply the Bayes theorem here? I want to know A given BC. Okay, based on this Bayesian formula, right? Anyone wants to take a guess? How would the answer look like? We'll try to solve it properly, but anyone want to guess how it will look like, the answer?
Maybe I'm making a wild guess. Maybe
Please,
probability
please.
of AB given C.
AB given C?
Yeah.
That's it.
Plus maybe probability of A. No, we are I'm not able to think further.
Okay. So let's apply Bayes theorem to this. I will do one thing. I will take this BCS one event called D. Is this fine?
Yes.
Can I? Yeah, right. I can take A and B as you know, Bhushan said. A and B is some event, right? Which is, let's say, I'll call it D. Now, so this is probability of A given D. Now, can you apply Bayes theorem on this? We know how to apply Bayes theorem on this, right? So what's the formula here for Bayes theorem?
Probability of A into probability of D given A upon probability of D.
Right. Okay. Now, probability of A, probability of B C given A, right? Probability of BC, right? Okay. Now, can I divide with probability of C on above and below? Or can I write this like this? P of A, P of BC given A, P of B given C into P of C. Is this fine?
Whether you have divided only on one side?
No, no. I just put P of BC as P of B given C into P of C.
Okay.
Yeah. So now, can I write this? So now, can I write something like, yeah. So this I can write now. This probability of C is now dividing this thing, right? So can I write this probability of B given CA divided by probability of B given C? Is this correct?
No, sir. I get confused here.
Okay. Fine. So okay. So the issue is this, right?
Yes.
How is this come? Okay. So we'll take one more approach. Let's say. So I'll write this as A given BC. BC, right? Is this fine? This becomes probability of AB C divided by probability of B given C into probability of C. This is again probability of AB given C by probability of B given C. Is this correct?
No, same thing. No, you written the same thing earlier.
No. Okay. There's some. Okay. Is this step clear?
Yes, that step is clear. Next is clear. That next only is question mark.
See, again, it's the same idea of conditional probability, no? What is conditional probability? Probability of A given B is probability of AB by probability of B, right? So now what I'm doing, I'm saying, okay, take this AB as some event, event, let's say D. This is example D. So what will happen? I'll have probability of DC by probability of C, which is probability of D given C.
Okay.
Right? And what is D? AB. Right? Now we just need to understand the. I'm sorry. So now, if you think about it, see what's going to happen. So this can now be written as I'll condition only on B. So I want A outside. I'll condition only on B, right? So what will happen? Probability of A into same thing. Probability of AB is there. Probability of A into probability of B. So this is going to become probability of A into probability of B, but this conditioning has to go somewhere. That comes here. Oh, sorry, conditioning on A also, right? So that's the thing. So.
No, sir. Probability of AB is equal to probability of A into probability of B. You cannot write because they're dependent. No, they're not independent. AB.
Not this. No, that's not right. This is probability of B given A, I meant.
Yeah, that is okay.
This idea we're using again here to divide this AB. So now think about AB as a AB as this, right? So you get probability of A here, and then probability of B given AC here.
Okay.
So so it will, yeah. So just take some time, but this is the idea. So the point is, if you have, so now all of these are conditionals only on C. So if you try to look at the Bayes theorem that we had before, so probability of A into probability of B given A by probability of B. So all this conditioning that you added extra, that is, let's say C was here, right? So C is added here, conditioning extra, that comes here and it comes here. So because P given AC, B given C and B given AC. That's how the Bayes theorem works for conditioned already conditioned joint solution. All right.
So what is the final form?
Yeah, this is the final form. So your probability of A given BC is probability of A, probability of B given AC by probability of B given C. So whatever was here, so now everything is in terms of C, conditioned on C. So here also you're conditioning on C. You want to look at B given A and probability of B given C. That's the idea. Yeah. Okay. Fine. So this hopefully is clear.
Yes, okay, it'll require some practice.
Okay, right. Yes. Fine. So yeah, so we'll move on to the next thing that I wanted to.
Provide this.
Sorry.
Can you provide this to us? Regarding
Yes, sir. Please hold it. We'd like to copy it. Just 1 minute.
Huh. So it's it. Uh, I take the PDF and put it in the this one, right? Link. So
Okay.
Okay. Sir,
yeah,
one general philosophical question.
yeah,
This Bayes theorem, if I try to understand, that is nothing but a conditional probability property. That is probability of A, joint probability of AB, P of AB is equal to P of BA, and each one expanding and then equating. And
right.
that is called Bayes theorem. I am just wondering, what is so insightful that I find it is nothing but normal conditional probability property. Why the Bayes got credit for what?
Yeah. So
But one thing, sir, tell me, before Bayes, conditional probability concept was there, right?
I'll have to go back to the history and come back to you. But see it would be there, but the idea comes in the terms of interpretation of these things actually more than anything.
Right. It is saying that like in mathematics, A
Uh,
dot B is equal to B dot A. So that A is equal to B dot A by A kind of. So I call it as Krishna's formula. No, I'm just joking, but it appears to me similar like that. Okay.
Yeah. See, I understand that the derivation may not be what you had hoped for. For example, when you had heard about the famous Bayes theorem, but the way ma'am also explained, I guess, in the thought process was this, right? So when you have something like this is where Bayes theorem brings credit to itself. So um, so let's say this is all your world knowledge before you got any information to you, right? This is something called as a prior, right? Prior knowledge that you might have. The point is, when you get some information, when you get some data from the world, how does your prior knowledge change, right? This is called posterior, and this is some, let's say, event or some knowledge, that new knowledge or new information that you got, right? This sort of looking at the Bayes theorem in this format, that is very powerful, because then this starts becoming this becomes a bedrock of things called as parameter estimation problems, right? Because there again, I guess you will go into neural networks a bit, but or let's say even your linear regression. The idea being that you have some prior assumptions about your parameters, let's say theta, right? And the point is, how do you incorporate that information that you have from the knowledge from the world? Now you got some data points. So how do you incorporate that information into making a better estimate of your, going towards the true value of theta, right? This is when you don't know anything about the world, right? So that relation is important. That is what lends the importance to Bayes' theorem, right? So it may be a disillusionment when you get to see the proof, but its importance in terms of how it is used, that is a simple matter. That's what I want to bring it out. Yeah.
It is like theory of relativity. Einstein got the credit. Lorentz and Poincaré had come so close that the transformations are called Lorentz transformations.
Right. Okay.
But he interpreted them in a larger framework and introduced the theory of special relativity. I'm speaking because I just saw the movie Oppenheimer.
Oh, okay. Fine. So I'm yet to see. So yeah, please no spoilers. Thank you.
So I feel it is a way of interpreting in the context of data science. I think that has assumed a lot of importance. Otherwise, it is mathematicians, but looks like a simple formula.
Right.
But the way you interpret it, like belief instead of probability, looking at data, the concept of post and prior, I think that is what goes credit to Bayes, not actually the formula.
Right. Yes. Yes. In that way, yes, you could think about that. So again, see, you might have heard about this central limit theorem and all of those theorems, right? So when you look at, so there is something called as Chebyshev inequality, Markov inequality, and all of those. So when you look at CLT as a special case of Markov's inequality, Chebyshev inequality, so you might feel it's, oh, that's it, is it? And that's the thing with knowledge. So once you know, magic, right? Once you know how the magic is done, you're no more you know uh, caught by it, right? So that's the thing I would say. So even before that, the point is that though the theorem may seem very straightforward, but the applications are, and more importantly, the interpretation is very different. And additionally speaking, there's also another interpretation. I would like to bring that to your thought process. So we discussed this last time also. Let's say we have this something called as y equal to f of x plus sig epsilon and something like that we were discussing. So we have this something called as the true function, right? And you're trying to estimate this true function with some estimator, let's say f hat of x, right? This is exactly what we were talking about last time. Now the point is, because we don't know this true function, but it is fixed. So this f of x is fixed, right? But unknown, right? So actually speaking, f of x is not a random variable, right? But the point being that we don't know what the value is. So that unknownness is now quantified as a probability, right? Is quantified as a probability. Now, this is a very big thinking change that you will need to do, because whatever you have learned till now, it's all okay. There is some random variable which has some distribution, and you try to make inferences about it, conditional inferences, and all of those sort of things. But this is not that form. Here, the idea is this is fixed. This is not random, but it is unknown. The unknownness is quantified using a probability. That unknownness becomes your prior. This is the unknown in this particular scenario. So that unknownness is quantified as a prior, and then you're trying to reduce or understand how much of it is still unknown. That new unknownness or whatever, right? That is quantified as this posterior probability and prior probability, right? So this is also another interpretation where, and this is where Bayesian Bayesian sort of thinking process, uh, uh, you know, wins over this frequentist sort of approaches, right? So it's more about how you can use this sort of thought process, right? So probabilities before, they were always thought about as something random, So I want to know its properties, but now it's not random, it's unknown. So that unknownness is now taken as probability, and you're trying to understand is what else is unknown about that true function or the true fixed parameter, right? That is a thought process. I hope this is clear.
Yes, sir.
Okay,
Yes.
fine. Um, so yeah, I guess this is all I wanted to say about the joint and conditionals. Okay, now yeah, so just on the using the previous thought process, can we let's try to solve this problem, right? So let's say I have a okay. So let's say I have a Bayesian network. Again, that's not necessary, but let's say I have this probability of f, I know is 0.1. Probability of c given f is 0.8. Probability of c given f bar is 0.3. Where f is basically having the flu and not having the flu. So it's a binary variable. And c is again coughing. Are you coughing or not coughing? Right. So with this, how can we find the probability of c? Any thoughts? I want to find probability of c and probability of f given c. Any thoughts?
P of C given F into P of F plus P of C given F bar into P of F bar.
Right. So that's basically we are doing the marginalization, right? Over all possible values that f can take, we're trying to look at this joint probability. Now this joint probability, since I have the conditional in terms of c given f, so what I can write it, I can write this as p of f into p of c given f, right? Joint condition probability formula. Now f can take either that is basically true or false. So that sort of a thing. So this basically just becomes probability of f into probability of c given f plus probability of f bar into probability of c given f bar, right? So this becomes just 0.1 into 0.8, 0.9 into 0.3, right? So 0.08, 7, I guess is 0.3, right? Now, how would you do probability of f given c?
In the first line,
Yeah.
You have written probability of P given C is equal to sigma over F. What is that? P into CF. That is C and F.
Yeah, C and F. So joint probability of C and F.
Okay.
So this is just your usual marginalization formula.
So that's equal to probability of P. Okay.
And this can be seen as a conditional. Yeah.
And last one is probability of the third line is probability of into probability of C into F, C given F plus probability of F into probability of C not F.
Probability of F bar into probability of C given F bar. So all
F
possible.
bar is equal to 1 minus F, right?
Correct. Probability of F bar is 1 minus probability of F, which we have. So I can just plug it as 0.9.
Oh.
Yeah.
Okay.
Sorry, probability of C is what? 0.08. No, Deep. So I guess this is clear, Deep, right? So only 0.35. Okay. All right. Now probability of F given C, how would we do that?
Bayesian formula.
Right, that's it, right? So C given F, probability of F, probability of C. Because now we have C, probability of C, we just calculated 0.35, right? So we can just put that values here, 0.8, 0.1, 0.35. You'll get something, some number, right? So hopefully this was clear, right? This is your usual application of Bayesian formulas.
Sir,
I mean, with network, the idea is that, sorry, go ahead.
Sir, kindly please repeat it once more.
Which part, Malati? The whole part? Sure. So if we see here, what we have is we have the probability of f, and we have the probability conditional probabilities of c given f and c given f bar. Again, this is very standard sort of way of talking about a Bayesian network, right? Because we only want the conditional probabilities, and that too at each node. So now what we want is we want the probability of C in general, right? And then probability of F given C. Now probability of C can be seen as a marginal over this joint distribution, that is C into F, right? Um, this is your marginal distribution, and then probability of C into F can be seen as product of conditional and the respective marginal. So this can be seen as probability of F into probability of C given F, the condition probability. So each joint joint distribution becomes this formula. Now the summation is over what? Summation is over all possible values that f can take. So let's say if f is yes, no, whatever, right? So in this case, f and f bar, right? Again, I'm sort of overloading the way it's written, but the idea is that this is probability of f, that's you are whatever having the flu, and then probability of cough having the flu plus probability of not having the flu with probability of cough not having the flu, right? That sort of a thing. So this is just your plug and play your formulas. Now what next we want is we want probability of f given c. F given c is so because now you have these respective probabilities, you can directly apply the Bayesian formula, Bayesian theorem, right? Which is probability of c given f into probability of f by probability of c. These are values we have with us, so just plug and play. Yeah. Is this clear?
Yes, yes. Thanks.
Okay. Next, what I had is, yeah. So naive Bayes, what is the assumption, by the way? What?
The features are independent of each other.
Sorry?
The features, the attributes are independent of each other.
That's it?
Yes. With reference to the label, the features are independent of each other.
Right, with reference to label. So conditional on the class, then they are independent. That's an important distinction to make. So let's say if I have n features, x1, xn, right? Then let's say if y is the class label that I have to predict, have, then this can be seen as probability of x1 given y, or multiplied with probability of xn given y. All right. So let's say let's say I know for a fact that let's say x2 and x3 are not independent given y. So then how do I handle in conditional base? Or let's say not naive base. How would you end up handling it, right? So and I want to motivate with one example. Let's say I'm sorry, if was somebody trying to say something?
So can you repeat the question once?
Yeah, so let's say for this is the assumption of naive Bayes, right? So let's say I tell you that okay, I know for a fact that x2 and x3 are not conditional given by, right? Then how do I handle it? One is your usual what is it called, Bayesian network. You'll try to do that here, right? That's one way of solving it, right? So one other way, or again motivated from Bayesian networks itself, which I wanted to give you an idea about this one example that I face in real life. So let's say I have theta as a random variable. Okay, so there's some p theta of theta, which represents an angle. Okay. So let's say theta is between minus pi by 2 to pi by 2, right? Now I take two functions of theta, that is sine theta and cos theta, right? So I have my two features, x1 is sine theta, x2 is sine theta, cos theta, right? So now, can someone tell me, is x1 independent of x2?
Yes.
Yes.
No.
No.
Okay.
Because
Uh,
cos square theta plus sin square theta is equal to 1.
I'm sorry.
Cos square theta plus sin square theta equal to 1.
Right. So let's say
No.
if I write it in terms of, yeah.
No,
So
given theta, x1, x2 are independent.
given theta, x1, x2 are independent. Why?
Because x1 is a computation is sine, x2 computation is theta, is cos.
Given theta, they're independent. You're saying, that is fine. Yes. Given theta, they might be independent. But I'm saying that I have two features. I have x1 is sine theta, x2 is cos theta. Are these two independent on their own?
Even given when you are given theta, once you know sin theta, you know cos theta. So
No,
how are they independent?
No, but if I give you theta, the values of sine theta, cos theta are fixed.
Okay.
So then in that sense, they are no more random, by the way. So therefore, they're independent of each other. It doesn't matter anymore.
They are independent, you are saying.
Yes.
Okay.
Theta. Oh, I might have to think about it. I'll come back to it. Yeah.
Yeah, because I think they are dependent. See,
Uh-huh.
is there any algebraic relation between two entities in an equation? Okay, then you can derive one from the other.
That is correct.
So
yes.
Then how can they be independent?
No, but you're looking in terms of the conditioning probability, no? The condition variables. That's the thing that
The
that's
x1 and values.
I'm sorry.
Here we are talking about the x1 and x2 values, right? Even
Yes.
if you know theta, sine form of theta gives you x1 value that would be entirely different from x2, then x1 and x2 would be independent. How can they are dependent?
No, they are different. Fine. So again, okay. So let's say S and C are the two variables that I have. So what is independence basically? Can I write this? If S given C is equal to P of S, then I can say S and C are independent of each other, right? Now, what who's the other person? So what they said was it's independent conditioned on theta. So what we need to look at is something like this: P of S given C theta, right? Is this equal to P of S given theta? And this is true. Does everyone agree that this is true?
Yes.
Okay. Okay, fine. So if I give you the theta value, let's say, if I give you theta value, what is the probability distribution of S? It'll be some single value, right? Sin theta takes one value for a theta, again in this range, right? So let's say if I give you theta as, let's say, 0 radians, right? So probability of S given C theta is going to be probability of S, right? Okay, so S is from -1 to 1 and sine 0 is 0. So it will be 0 with a peak here. This peak length being exactly equal to 1. Right? Now, if theta is 0, I know cos theta is 1. Right? This cannot take any other value, by the way. Right? So if I know theta is 0, cos theta is 1, sin theta will always be equal to 1. So it doesn't matter. So if I know C, so I'm telling you, okay, so it's like telling this. I'll tell you theta and I will say the cos theta value. By not knowing cos theta value, will it affect the value that I know about sin theta? Will it? I'm asking a question.
No.
Right. So even if I don't give you cos theta value, because I'm giving you theta, Sine, you can know the complete distribution of the sine variable just by knowing what theta is. I don't need to know cos theta at all. So conditioned on theta, sine and cos are independent. That was right. Is that convincing? Any other thoughts here? Anyone wants to contribute anything here?
Actually, sine theta and cos theta, when we take, once if I know sine theta, definitely I can predict cos theta, right? So then they are not independent.
Again, so we are not discussing about sine cos only. We are discussing about given theta.
Theta, yes, of
So
course.
theta is given. So if I give you theta, okay, I can know the sine theta value without any confusion. And if I give you additionally cos theta value also, will that make any difference in the value that you thought that sine theta will take?
No, sir. No, sir. For only theta is required. We give theta, the mystery is solved.
Right. So if I give you theta, as you said, the mystery is solved. So if I give you additionally cos theta, it doesn't matter. This is exactly what this relation is capturing. So probability of S given C theta depends purely on probability of S given theta, because sine can be completely understood if I give you theta. I don't need additional this random variable cos, which will affect my distribution of sine variable. Is that clear?
Or, sir, we can also express S is equal to sine of cos inverse C. Then in that case, it is purely dependent on C.
We'll come to that. But that's not the question. The question is given theta. Given theta, they are independent. All right. Okay. Now we'll come to this idea. So now let's say if I give you probability of sine S given C, is this equal to probability of S? I don't know theta. Is this true?
No.
This is not true, right?
Not
Very clearly, right? Because the point being, so let's say sine theta is some value between -1 to 1, right? Immediately, as soon as I give you the value of cos theta, let's say I tell the value of cos theta is 0. Immediately, you can make some assumptions about what sine theta this S variable will take, right? Which is plus or minus whatever, root of 1 minus S C square, right? So that's the thought process. So here, P of S given C is not equal to P of S. So it does depend upon the cost value. The distribution of S will depend on the cost value. So let's say if you know these sort of relations, then how would you handle something like this? Let's say I have P of you know um, so probability of SC, these two variables given some class, let's say Y, right? So this will clearly violate the the naive Bayes assumption, right? So I cannot write this as probability of S given Y into probability of C given Y, right? Regardless of any label, this will always be, they're always dependent. And again, somebody mentioned that they're orthogonal. That is correct. Orthogonal is fine, but they are not independent. That's the thing that we're trying to understand. So now this, so how would you solve this? If you had to, for example, work with these two variables? How would you model something like this for your naive Bayes problem statement that you have? We just discussed this, right? I have a conditionally joint distribution. So because we cannot assume this independence, very simply, the idea is this just becomes probability of C given Sy. Right? You'll have to model the complete conditional distribution. So what you'll have to do, what you will do is, let's say for a given class, you'll find the probability of S being taking some value. For this, you will need the sign value also, right? Or this is, in a way, you can write like this: C of C given by into probability of S given C by. All right, is this clear?
Yes, sir. Little practice is needed.
Yes, yes. So yeah, conditional probabilities, joint probabilities, joint conditionals. So this will take some time, but make sure you do this routinely, right? Try to see as many problems as possible. Okay. One final thing which I wanted to mention, for example, let's say, so Bayesian networks. Again, ma'am discussed this, right, in the this one in the um, lectures. So, what are two main properties of Bayesian networks in terms of its graphs? Graphical
Directed
properties.
acyclic graph.
Correct. It's a DAG and
And the joint probability of all the variables is a multiplication of individual probabilities, conditional. Yeah.
conditional one. Yes, correct. Yes. So, but this myself I've forgotten. Uh, right. So yeah, direct acyclic graphs. So basically, there should be no cycles, and there should be directed edges only are allowed. Right. And you're right, so then if you mention it like this, what you can do is you can write the complete joint distribution in terms of the conditional distributions which are given by these edges. So again, some routine simple questions on uh, graph properties, right? So let's say, so my question is, let's say what are the parents of C in this graph?
A and B.
Okay. And what are the children of C?
D. D and D.
D and E. What are the descendants of C?
D and E.
D only, no.
I'm sorry.
D and E.
Okay, just a moment. Just a moment. Um, so you said descendants are just D and E, is it? No, no,
And
the
one below, and K and J.
A and J, is it?
K.
A and K.
K and J.
K and J. Yes.
K for
Yes.
Kolkata, J for Jamshedpur.
Yes. Yes. So descendants basically mean your all the children of all the childrens, right? That's the idea. Okay. So just a moment. I need to.
There is a question on what is called this outside Markov circle, but it is not mentioned anywhere in the video.
Okay. Uh, yeah. Just a moment.
Yeah, that is Markov blanket.
Markov blanket.
Yeah, just a moment. I need to set this up. Fine. That won't happen today. Okay. So where were we? Yeah. So we had C, A, and B, and then let's say D, E, F, and G. So descendants basically will have all of these D, E, K, and J also, right? So then, what are non-descendants?
F, G, I, and what is the other one on the left hand side below G?
H.
H.
Yeah. So descendants were D, E, K, and J. So non-descendants, yes, is basically G,
H, F, I.
H, F, and I. Right? Yeah. So one property that is mentioned, I mean, in Markov, sorry, in Bayesian networks, is this, right? That is your any node is conditionally independent of the non-descendants given the parents, right? So let's say if I want to understand P of C given, let's say A, B, G, and I, for example, right? This can be seen as property of C given AB, because the fact that if a condition on the parents, all the parents should be there. If a condition on the parents, then any of these non-descendants don't matter in the probability of this C. So, so therefore, if I specify this probability distribution, this probability table in some sense, I'm fine. I don't need to look at the other possibilities. Now, somebody mentioned something about Markov blanket, right?
Yeah.
So Markov blanket. Is just a moment. Right. So Markov blanket is the parents of a node, the children of a node, and the children's parents, other parents basically. Right. So something like this. So this will be the blanket of C. So the parents, right, that is there. Then children have to be there, right? Children are there, and then the children's parents. So E has another parent F, D has another parent G. So this becomes the blanket of C, right? And what the rule of, I mean, the Bayesian network tells you is that probability of C given its Markov blanket, and any other node, right? Any other node in the whole system is just equal to probability of C given its Markov blanket. So if I give you the Markov blanket, then any other node is conditionally independent of the node that is under discussion, right? So this is another property of Bayesian networks. Right?
That means H, K, J, I have no impact on the probability of C.
Have no impact on the probability of C given the Markov blanket. This is always important. The conditional statement have to be taken into consideration. Yes. Because see, this is exactly the same discussion we had regarding the sine and cosine given theta example, right? So if I give you theta, then sine and cosine are independent, right? But if I don't give you theta, very clearly they are not independent; they are dependent. So therefore, if I give you the Markov blanket, then other nodes in the Bayesian network will not have any effect on the probability, this conditional probability at least, right? Yeah. Somebody raised a hand. Is it?
What is the probability of C in this case?
Sorry.
What is the probability of C in this case, sir?
In which case?
C is having the parents A, B. So in this
Right.
case, how can he calculate parent probability of C?
Okay, how do you calculate the probability of C? But okay, the point is this: if you want to calculate the probability of C, you actually will frame it as a marginalization problem first. So you will say all A, B, etc., everything, right? Until what is the thing here? K, J, K, H, right? Something like this. Now the second, right? So okay, this summation is over. the summation is over A, B, D, E, etc. until H. C will not be summated here, right? Obviously, right? Then now I can write this as sigma over probability of C given A, B, and all of those remaining elements into probability of A, B, and all of those elements, right? Now the point is, if I so now I need to look at the Markov blanket of C, right? Because then I have all the other nodes here also. So probability of C given, this will become probability of A, B, G, D, E, F, right? A, B, G, D, E, F only, right? Because here I have A, B, C, D, E, F, G, H, I, O. It's all until J, is it? K. Oh God. One second. So until K. So K, and this is also K, right? And then again same thing here, right? A, B, D, E, F until K, right? Now, so this probability can become simpler because A, B, G, D, E, F is the C's Markov blanket. Then now this one you will need to again break it down and then keep on going like that. That's the idea of if you want to know the probability of a single node in this whole array of things, right? Or the other way you can do is, as somebody said, right? So this basically the joint probability of this whole Bayesian network, right? So what is the joint probability of a Bayesian network? How do I express that? Sonali Das, you can try to answer. How do I explain the joint probability of a Bayesian network? So anyone want to take a guess? No. Okay. So basically, I can look at it as probability of this A into probability of B, probability of C given AB, right? And then probability of all of these, parent conditions and everything, right? All of that you'll have to expand, and you'll have to summate over all these other nodes A, B, D until K. You will not summate over C, right? That's how you will look at this, probability. Okay.
Yes,
Sorry.
Do you have any resource, maybe on the internet or somewhere where all these things are given in a concise way? Because these are not in the slide, I mean the videos, and we don't have any, and the textbook is too cryptic. So some other resource where they can, all these formulas are written and the derivations are written, so it can sinks into your mind and we can practice it.
Yeah. Again, so I don't deal with Bayesian networks that much, so I don't have a textbook off the top of my head. I'll have to check. And I remember last time you guys asked for something on the overfitting, underfitting, and all of that. I'll get back on that also. I'll have to check. Not yet. I don't have anything yet in my head. Yeah.
Sir, shall I give an advice?
Yeah.
Sure.
Things we remember done in school. I am actually a senior citizen, but now to make sense of each of these things, I used to go to tons of YouTube videos. People explain simply with some examples in the concepts. So for every 1 hour of madam's video, I had to at least watch 3-4 hours of supplementary videos to make sense of probability concepts. There is nothing like patience and hard work, sir. It's really it's a head twisting first time when you particularly probability concepts.
Yeah.
Particularly the conditional probability concepts, because most of the books do not give real life examples.
Yes. See, why we understand the frequentist approach is that is conceptually easy. Like frequency total number, the actual number by total number. But here everything is conditional. Conditional means what? Conditional and chaining. Actually true. It's a really tough. I think YouTube has a lot of examples, sir. People, because I watch a lot of YouTube videos, at least I could say I could get sense of 60-70%, but I don't say I'm still confident. I have to at least watch another 10 hours or so video to make sense of it and work out a lot of examples. There is no other way.
Because this week is quite the toughest lectures, toughest content.
In fact, I would say that all machine learning is actually based on the Bayesian probability. So I think it is worth spending more time getting the core of these Bayesian concepts before we can make sense of anything in machine learning.
Okay.
So shall we do one thing then? So the Monday and Tuesday we still have two, TA sessions left, right? So I can ask them to do like one topic in detail or something like that, if that's something that you guys want, right? For example, let's say Bayesian networks. If that's not clear, then we can take it even more slow, through by through. We can have even both the TA sessions on the Bayesian networks. So that is also fine. I mean, I can make a suggestion, and then the other TAs can, take.
That's fine.
That's good thing, sir, actually.
Okay, fine. So I'm assuming, okay, so this week we actually had what all? So we had Bayesian learning, naive Bayes, and Bayesian network. So I'm assuming Bayesian network is where you guys are facing a bit of a problem, right?
Yeah, and a little bit of naive Bayes.
Naive Bayes. Okay. Okay, so I'll ask both of them. I'll request both of them to do Bayesian networks in more detail, right? Probably going slowly, step by step. Probably, yeah. That might help. So because I mean, so man's video is like half an hour. So but here you'll have like 4 hours pure Bayesian networks, and that too you can ask questions, get each and every doubt cleared. Will that help?
Yeah.
Yeah, definitely, sir.
Yes, sir.
Okay.
Some
Okay.
numericals, sir, if possible.
Numeric problems. Okay, sure. We can arrange that. Sure.
Thank you, sir.
Okay, good enough. I guess this is at the end. There was one concept that I wanted to introduce to you all. And okay, just give me 2 minutes. I'll just give you the brief idea about where I'm coming from. So, in all these examples, and even Krishna, I guess, mentioned this idea that frequentist approach is basically just frequency. Take the required number by total number, you get the probability. So this is something that you need to keep in mind. For example, let's say there is some true process, right? Which let's say spits out ones and zeros. Okay, which is basically a Bernoulli random variable. If you're not aware of this, Bernoulli random variable. Now, so this random variable has a parameter called p. That is the probability with which ones will come, and 1 minus p is the probability that with which zeros will come from this random variable. Okay. So then think about this idea that so now the question is, how do I know this p, right? The true p, for example, right? I want to know the true p. So but what you have from this random variable are only examples. Like your sampled this random variable, let's say 10 times, 1,000 times, or whatever. So you have, let's say, 1,000 values, binary values, right? 1,000 binary values. Now the point is, how do you get this true p? One very simple idea is that I can just average these 1,000 binary values, right? Because p is what? P is the fraction of times ones will come. Now the fraction of times ones are in this is basically could be the true p. Is that correct?
Correct, sir. Correct.
Okay. So now let's say you got some fraction. Let's say I'll call this p hat. Okay. Now you need to understand one point. Again, this is exactly what I raised last time also. This p hat is what you calculated from the data, right? This may not actually be the true p. Okay. So this is we call something called as an estimate of. Okay. This is
Are
the true.
they current running data? How we will predict this data?
No. So I'm
Any
saying that.
data that
So, so,
is
so, so you have the data with you. Some with some sampling process, you could get 1,000 values from this random variable, right? And 1,000 is max. You cannot go even more than that. Let's say, right? Now the question is, okay, then what is this p that exists in this true random variable that you had, right? That's the question we're trying to answer, because the data is always finite. This is, you need to understand, this data is always finite. You can't have infinite data. So with this finite data, you will estimate, you will just take the fraction of times you found ones in this, right? And that could that will basically, let's say, called p hat. This p hat is not the true p, that you need to understand. This is an estimate of p. So all those in these knife-based problems, where you were calculating the frequency, number of values by total number of values. Last time we were doing that entropy calculations, right? Where we were looking at that entropy, that fraction of times the target variable was coming. All of that. Those are all again just estimates of the true probability. We don't have the true probability at our hand. Okay, this shift from thought process is required. And then the next question comes, how good is this estimate? Right? How good is this estimate? That's where a lot of statistics goes into picture to understand, to know how good this estimate is. Okay, so I'll leave you with this thought process. Whenever you're taking frequentist approaches and all of that is just an estimate of the true probability. You cannot get the true probability, even though if it is fixed, but it is unknown. That's the ending point I wanted to make. Okay.
Sir,
No,
the confidence belongs to the same concept, right?
Right.
We can only arrive at confidence interval, but absolutely never 100% confident.
Correct. So you can, this goodness of estimate comes in many different forms. One of them is confidence interval.
Let us take a simple example. There are only two balls in a urn. One is red and one is black. Can't we say that the probability of pulling out a black is 1/2, and there's no question of confidence interval. This is the true one.
Correct. But so there the true nature of the world. That is fine. So then you have the access to a true random variable. But this, you don't have the access to the random variable. You only have access to samples from this random variable.
Okay.
That's where the question comes. And this is exactly
what might happen is, sir, what might happen is, even though we have red and green ball, we don't know about red and green ball. Even if we draw 1,000, it may so happen that all the 1,000 may be red only.
Yes.
It's also possible. Right.
Correct. Yeah. Precisely. So as you said, the Bhushan, yeah, right. So as you said, like there are some, let's say, two black balls and two red balls, for example, in the bag, but you don't know the bag. The bag is, let's say, covered in complete black and everything. What you can do is you can always try to get one ball and look at its color and then keep it back, right? Something like that you can do. So this is basically your true probability. What you get, the samples from this, you're taking one value, taking one ball, looking at it, giving back, taking one value, giving back, and so on, right? That is basically samples from this. You're drawing samples from this distribution. Now it may so happen, as Krishna said, that all of the samples that you drew ended up having only black balls. So what you will say, oh, the probability of black coming is 1, but is that the true value? No. But you also need to account for the fact that, let's say I drew 1,000 samples, right? What is the probability that all 1,000 will come out to be blacks? The probability of this event happening itself is very low. right? That is where you can make some good estimate about, okay, whatever value I got, is it even close enough to the true value or not? And again, under some assumptions, that's how you will arrive at this things called
That
confidence.
means you are saying that the frequentist approach works if you know
Yeah.
your universe accurately.
Your frequentist approach works because it gives you something which you can estimate. At the end
Which
of
you,
the day,
yeah,
if you have to work with something, you need some number, you need something. And there are some theoretical justifications for frequentist approaches also. But what you always need to remember is that they will always give you an estimate. Don't believe blindly that that's the true value.
Sir, in that case, most of the machine learning algorithm, I think it is just an estimate only, right, sir? What we get is not a true value.
Yes, precisely, precisely. That's exactly what we were discussing last time also. If you remember, we had a true function f of x. I was saying, okay, f hat of x and all of that. So this is the estimate of this true function f of x. So this is what you can learn. This is what we do in machine learning. This is the max we can do. What we need to go from is we need to understand how good is this with respect to the true function that is fixed but unknown. Yeah.
okay.
Is it the cause behind is we are dealing with the images and that is mostly made up of pixels, or is it because of the data running motion data, or how we predict?
I'm sorry. There was some network issue. Could you repeat your question?
Actually, here everything is prediction, right? It's a probability. Then I would like to ask you the reason behind is mostly it is dealing with the images data, imaging data that would be in the form of pixels. Is it because of that, or the data of motion data? So.
No, no. See, again, this example has nothing about imaging. No, if you think about it, there is no image, there is no pixel, there is nothing here. This is this is one true, one way of sampling some random process, right? So there is some bag you're sampling from this, and that's the question. Now that the point is, because you have finite samples, you can never know what the true value is. Whatever you get is an estimate.
That is analog to digital?
I'm sorry?
Analog to digital, is it so?
No, no. See, again, there is no analog digital here, right? Subhashini, see, the point is you have four balls in the bag. There are two red, two black, right? What I'm doing is the bag is completely black. I don't know anything about what is there inside the bag. What I can tell you is you can put your hand into the bag, you can remove the ball, look at its color, keep it back. You can do this 1,000 times. Now the question is this: can you tell me how many blue or sorry, red or black balls are there inside the bag truly? Can you ever do that? That's the question. You cannot.
No, yes, sir.
Analog, digital, there is no image, there is no speech, there is no text, there is no numbers. It is just the question of, do you have the whatever samples you get, are you sure that whatever number you get is the true number or not? The point is you can never be sure.
Yes, sir, I got it. So I'll give my interpretation. For example, using the same bag, let us say you drawn 1,000 samples.
Right.
It is very rare out of 1,000, there will be 500 black and 500 white. That is also rare. You will get probably 499 black or 501 as close to half probability rather than exactly 500 black balls and 500 white balls. Am I correct?
Right. Correct. So if you remember, there is I mean, if you know, there's something called as Bernoulli binomial random variable, right? So what is binomial random variable? Basically, you're looking at let's say if I run a Bernoulli random variable, let's say n number of times, what is the distribution of those n values? So as you said, the probability distribution will be something like this, right? So where the probability of getting 1,000 blacks, probability of getting 1,000 reds, and this is the probability of getting 500 blacks and 500 reds, right? So the probability is very high. So but the point, let's say you might get, let's say, some 480 blacks, or let's say 80 blacks, right? So then the question becomes, okay, though you got this, but what is the probability of getting such a number itself, is that high or low? And that's how you'll make inference back about your true probability. All right.
Okay. One question to all. Do you have any idea whether we are having a 2-hour exam or a 3-hour exam?
It's a 3 hours, sir. Typical NPTEL exams are all 3 hours.
No, there are many are 2 hours. For 12-week course, it is 3 hours. I don't know for 8-week course how much it is.
No, I know I've written NPTEL, but all NPTEL exams I wrote are 3 hours.
And all courses for 12 weeks.
Whether it is 12 weeks or 8 weeks, they give 3 hours time.
Okay. So we have to study hard.
Sir, study smart, sir.
Study smart and hard. Even I gave my last exam some 25 years ago.
Sir, I am also like to see earlier Ravindran sir class I have attended, but I find that this madam's class is relatively easy in the sense, okay, to make sense of it lighter on our brain.
So I'll stop the recording just a moment.